Alright, welcome to Engineering 270 Lecture 10. So today we're going to talk about something called pulse width modulation. And this is a way that we can do things like pretend that we can put out a voltage between 0 volts and 5 volts. Now normally in our digital world everything is a 0 or a 1. And 0 is typically 0 volts, and on our PIC system and in Engineering 250, a 1 is positive 5 volts. Well, suppose we're trying to drive a motor, and a motor basically you hook it up to a battery and the motor spins. And generally, the higher the voltage of the battery you hook up to it, the faster the motor is going to spin. A 5 volt source connected to a motor will tend to spin pretty fast, and if you connect 0 volts, of course, the motor doesn't spin at all. What if you want the motor to spin at half speed? One option would be to somehow output 2.5 volts, and the motor would spin roughly at half the speed. But on a digital device like the PIC processor, we can't output 2.5 volts. We can output 0 or we can output 5. But we can do something almost as good. We can do the following. Instead of just putting on an output at 5 volts, which runs the motor at full speed, we can modulate the output. We can alternate between 0 volts and 5 volts. And if we do this so that 50% of the time we're putting out 5 volts, and 50% of the time we're putting out 0 volts, the effect on the motor will be it will run basically at 50% full speed. It will act as if we were putting in halfway between 5 volts and 0 volts. And this may not make sense to you. What we're really telling the motor to do is go at full speed and then stop, and then go at full speed and then stop. And that doesn't sound like a motor running at half speed. But if we do this quickly enough, the physical aspects of the system will smooth out this variation between being on all the way and being off all the way, and it'll end up spinning at about half speed. So we need to make this total time that we're on and then we're off something fairly fast, maybe a millisecond, for example. I mean, if we turn it on for 5 seconds and turn it off for 5 seconds, it's going to spin up and then it's going to slow down and spin up and slow down. But if we make this pulsing happen very quickly, for example 1,000 times per second, the motor will smooth out these variations and it'll spin at half speed. And this is something called pulse width modulation, or PWM. And PWM is used to control motors with computers when we want to do things like change the speed of them. You can hear this on subway systems. They use PWM at about 100 hertz, and you can actually hear some of the frequencies when they're changing the speed of the motors. Now, this is going to run the motor at approximately half speed. If we were to do something like this, so I have a waveform here where the motor is on for 75% of the time and it's off for 25% of the time. This motor is going to run at about 75% full speed. And it kind of makes sense because it's getting its 5 volts for more time than it's getting the 0 volts. So you'd expect it to run faster than this, but not quite as fast as this. And we can go the other direction as well. We can have a motor that's mostly off. It could be off for 75% of the time, and then on for 25%. And that's going to be running at about 25% full speed. So all of these are basically the same frequency. I haven't drawn them exactly the same, but they could all be toggling between the on state and the off state and going back to on every millisecond. It's not a function of frequency, it's a function of how long the waveform is high versus how long it's low. And this is something called the duty cycle. And the duty cycle is usually how long it's high versus the entire duration from one pulse to the next. So this is a 50% duty cycle. This is a 75%. This is a 25%. Up here, if the motor is just on all the time, that's 100%. And if the motor is completely off, if it's always at 0 volts, that's 0%. So duty cycle is on time over the total period. So this is the total period, and this is the on time. And this is a general concept. We use this anytime that we want to use a digital device to control something that's more analog, like a motor that is able to run at something more than just full power or no power, has levels in between. We can use this with LEDs, right? LEDs are always either on or off. You put in enough voltage and they turn on and they're very bright. And if you go below that voltage, they turn off and they're completely dark. So how could you make an LED run at half intensity? You can use pulse width modulation. If you send 5 volts and then 0 volts and alternate back and forth 50-50, that LED will look like it's half as bright. We can use this to drive a speaker, right? If we want to make a speaker that reproduces analog sound, we have to be able to send in something other than just high voltage or low voltage, 5 volts or 0 volts. We want to move that cone of the speaker a different amount depending on the intensity of the sound we're trying to generate. Well, we can do that with pulse width modulation. This is what the old Sound Blaster sound cards did in the early PCs. They were digital, but they acted as if they were able to send out analog information by using this pulse width modulation. So pulse width modulation is a generally useful technique, and we can do this with what we already know on a PIC processor. We know how to turn on a bit in latch A, we could say bit set, and we know how to turn it off, we could say bit clear. And we have access to timers. We can do timing loops, or we can set up the timing subsystems, and we could say, hey, let's wait for half a millisecond and then generate an interrupt, and wait another millisecond, generate an interrupt, and each time we get an interrupt, let's just toggle the output value. Or we could say, wait for 0.75 milliseconds, and then when you get an interrupt, clear the output and set your timer for 0.25 milliseconds. And then when you get an interrupt, set your output high and arm an interrupt for 0.75 milliseconds. And when you get an interrupt, set the output low, and so on. So we can do this, but that's kind of inconvenient. So on the PIC processor, there's a system built in. It's called the Enhanced Compare, Capture, and Pulse Width Modulation module, so ECCP. And the ECCP module can do a lot of things, but we're only going to use it for one thing. We're going to use it to generate pulse width modulated waveforms. Alright, so next lecture we'll look at the ECCP modules and see exactly how to set them up to do this kind of generation.